The morning of July 19th, 1944, Göttingen, Germany. In a heavily camouflaged hangar at the Aerodynamische Versuchsanstalt research facility, 3 Luftwaffe aerodynamic engineers stood before the skeletal remains of what had once been Lieutenant Thomas Fraser's P-51B Mustang. The aircraft had been disassembled methodically, its panels removed with surgical precision, exposing the internal structure that German salvage teams had transported from occupied France just weeks earlier. The wing lay separated from the fuselage, mounted on specialized supports that allowed detailed examination from every angle. Oberingenieur Klaus Doetsch, chief aerodynamicist at the facility, ran his measuring instruments along the wing's leading edge with the practiced movements of a man accustomed to discovering secrets hidden in metal and mathematics. What he was documenting would force German aviation designers to confront an uncomfortable truth about American engineering, capabilities that contradicted everything the Reich's propaganda had proclaimed about inferior enemy technology and industrial methods. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The Mustang that now lay disassembled before these engineers represented more than captured enemy equipment. It embodied a fundamental challenge to German assumptions about aerodynamic design philosophy that had governed Luftwaffe fighter development since the war's beginning. Within days, Doetsch and his colleagues would produce technical reports that circulated through German aviation establishments, documenting not merely what the Americans had built, but how they had managed to achieve performance characteristics that seemed to defy conventional wisdom about fighter aircraft design compromises. This particular P-51B, bearing the remnants of its squadron code QPG and nicknamed Jerry, had crashed near Rouen on the 6th of June, 1944, the very day Allied forces stormed the Normandy beaches. Lieutenant Fraser had survived the forced landing, becoming a prisoner of war. His fighter, however, embarked on a different journey into captivity, one that would expose the sophisticated engineering thinking that American designers had embedded in every curve and contour of its revolutionary wing structure. The story of how this Mustang came to rest in pieces within a German research facility begins not with Fraser's crash landing during the chaos of D-Day operations, but with the escalating technical arms race that characterized the air war over Europe and the desperate German need for accurate intelligence about Allied aircraft capabilities that transcended fragmentary combat reports and second-hand accounts from pilots whose observations reflected the confusion of aerial combat rather than systematic engineering analysis. By mid-1943, German aviation designers faced a strategic crisis that threatened their ability to develop competitive fighter aircraft despite considerable technical expertise and advanced wind tunnel facilities. American bomber formations penetrated deeper into the Reich with each passing month, protected by fighters whose true capabilities remained partially mysterious to engineers who had to make design decisions based on incomplete and often contradictory information gathered from combat pilots, whose reports varied wildly, depending on circumstances, altitude, and the chaos of engagement. The Luftwaffe had established sophisticated systems for recovering crashed Allied aircraft across occupied territories, with specialized salvage battalions working methodically to secure crash sites and transport repairable machines to centralized testing facilities before advancing Allied forces could recapture the wrecks. The organizational structure reflected German military thoroughness even as resources grew scarcer and the overall strategic situation deteriorated. These recovery operations operated under constant time pressure, knowing that Allied air superiority meant fighter bombers could appear at any moment to strafe and destroy captured equipment before it could be transported to secure locations. Göttingen's Aerodynamische Versuchsanstalt, established decades before the war as one of Europe's premier aerodynamic research centers, had become increasingly involved in evaluating captured Allied aircraft alongside its traditional role, developing German aviation technology. The facility possessed wind tunnels and testing equipment that allowed engineers to conduct detailed technical analysis under controlled conditions, providing data that supplemented but could never fully replace actual flight testing conducted at facilities like Reich, the Luftwaffe's primary flight testing center located approximately 100 kilometers northwest of Berlin. Fraser's Mustang arrived at Göttingen in remarkably intact condition considering the violence of its forced landing on French soil. German salvage teams had worked efficiently to disassemble the fighter into transportable sections, carefully documenting the removal process to facilitate later reassembly if required. The aircraft was one of several captured P-51 seconds that German technical services had acquired through the statistical inevitability of thousands of Allied sorties flown over occupied Europe, where mechanical failures, battle damage, navigation errors, and fuel exhaustion resulted in numerous forced landings that left machines largely intact and available for detailed examination. The engineers at Göttingen approached their examination of the captured Mustang with professional curiosity tempered by pragmatic understanding that whatever they learned would come too late to fundamentally alter Germany's deteriorating strategic position. Nevertheless, technical intelligence gathered from captured aircraft provided valuable information that might improve German fighter designs, inform tactical decisions, and perhaps most importantly, offer realistic assessments of Allied capabilities that cut through propaganda and wishful thinking that had characterized much official discourse about enemy equipment and industrial capacity. When Doetsch and his team began their systematic examination of the Mustang's wing structure, they immediately recognized something extraordinary about its design philosophy. The wing profile diverged dramatically from conventional German practice in ways that suggested American designers had embraced theoretical concepts that German engineers understood intellectually, but had not implemented operationally due to manufacturing constraints and conservative design philosophies that prioritized proven solutions over experimental approaches. The wing's cross-sectional shape revealed a laminar flow airfoil design that positioned maximum thickness substantially farther aft along the chord than traditional airfoils employed on Messerschmitt and Fokker-Wulf fighters. This was not simply a matter of aesthetic preference or minor aerodynamic refinement. It represented a fundamental reconceptualization of how airflow should behave across a wing surface at high speeds, prioritizing drag reduction through maintenance of smooth laminar airflow across a greater percentage of the wing chord before transition to turbulent flow occurred. German aerodynamicists understood laminar flow theory perfectly well. Research conducted at facilities like Göttingen and the Deutsche Versuchsanstalt für Luftfahrt in Berlin-Adlershof had explored these concepts thoroughly in wind tunnel testing during the 1930s. The National Advisory Committee for Aeronautics in America had published research on laminar flow airfoils that German engineers had studied with professional interest. What separated theoretical understanding from practical implementation, however, was the enormous manufacturing precision required to achieve the aerodynamic benefits that laminar flow airfoils promised. Laminar flow airfoils demanded extraordinarily smooth wing surfaces with minimal discontinuities, irregularities, or imperfections that could trigger premature transition from laminar to turbulent flow. Even minor surface roughness, poorly fitted access panels, protruding rivet heads, or accumulated dirt and insects could destroy the carefully designed pressure distribution that maintained laminar flow. German manufacturing techniques, optimized for rapid production under wartime conditions with limited skilled labor and increasing material shortages, struggled to achieve the surface quality that laminar flow designs required to function as intended. The Americans, Doetsch and his colleagues now discovered, had not merely designed a laminar flow wing in theory. They had actually manufactured it with sufficient precision to make the concept work in practice under operational conditions. This represented a stunning achievement in industrial engineering that spoke volumes about American manufacturing capabilities, quality control processes, and the integration of advanced aerodynamic theory with practical production methods that could deliver consistent results across thousands of individual aircraft. Detailed measurements of the Mustang's wing revealed the NACA 45-100 series airfoil profile that North American Aviation had developed cooperatively with the National Advisory Committee for Aeronautics, specifically for the fighter. The maximum thickness occurred at approximately 50% of the chord length, significantly farther aft than the 30 to 35% position typical of conventional airfoils used on German fighters. The leading edge radius was carefully shaped to maintain favorable pressure gradients, while the upper surface contour was designed to support extended laminar flow by avoiding the rapid pressure changes that would trigger boundary layer transition. More remarkable than the airfoil shape itself was the precision with which North American Aviation had executed the manufacturing. The wing skin panels fit with minimal gaps or steps between sections. Rivet heads were flush-mounted and carefully fared into the surrounding surface. Access panels incorporated thoughtful sealing arrangements that maintained smooth external contours. The entire structure reflected a manufacturing philosophy that prioritized aerodynamic performance through attention to seemingly minor details that accumulated into measurable drag reduction and performance improvement. German engineers measured the wing's surface roughness with specialized instruments, documenting finish quality that exceeded what German production facilities typically achieved under wartime conditions. They carefully mapped the pressure distribution across representative wing sections, correlating measured results with theoretical calculations to understand how effectively the design maintained laminar flow at various speeds and angles of attack. Wind tunnel testing of captured wing sections provided data under controlled conditions that complemented field measurements taken from the intact aircraft before disassembly. The technical reports that emerged from Göttingen's examination made sobering reading for German aviation designers and military planners who understood their implications. The Americans had not achieved the Mustang's exceptional performance through revolutionary engines alone, although the Rolls-Royce Merlin power plant certainly contributed substantially to the fighter's capabilities. They had combined that powerful engine with an aerodynamically sophisticated airframe that minimized drag through careful attention to every element of the design, from the laminar flow wing to the innovative cooling system placement that actually generated slight thrust rather than pure drag. This integration of advanced theory with practical manufacturing capability represented exactly the kind of comprehensive technical achievement that Germany's fragmenting industrial base and deteriorating resource situation made increasingly difficult to replicate. German designers could certainly understand what the Americans had accomplished. They possessed the theoretical knowledge and wind tunnel facilities to explore similar concepts. What they lacked was the industrial stability, material availability, skilled workforce, and time required to translate theoretical understanding into operational aircraft that could be manufactured in meaningful numbers with consistent quality. The Göttingen reports documented specific measurements of the Mustang's wing geometry, noting the chord length at various stations, the thickness distribution from root to tip, the precise airfoil coordinates that defined the cross-sectional shape, and the exceptional surface quality that made the laminar flow concept work in practice rather than remaining purely theoretical. These measurements circulated through German aviation establishments, informing designers about Allied technical capabilities and providing realistic data for comparison with German fighter development programs. Doetsch and his colleagues noted particularly how the laminar flow wing contributed to the Mustang's exceptional range that made strategic bomber escort missions possible. Reduced drag at high speed meant the fighter burned less fuel for given performance, extending range without requiring impossibly large fuel tanks that would compromise other aspects of the design. The Americans had solved the fundamental problem that had plagued fighter development for years, the brutal trade-off between range and maneuverability, not through revolutionary breakthrough in any single area, but through careful integration of multiple incremental improvements that accumulated into decisive operational advantage. The wing's structural design also impressed the German engineers examining it. The main spar carried loads efficiently through a deep section that provided strength without excessive weight. The computation skin was stressed to share structural loads, a design philosophy that German engineers understood but had implemented differently in their own fighters. Ribs were spaced to support the skin adequately while minimizing structural weight. The overall design reflected sophisticated structural analysis that optimized the balance between strength, weight, and aerodynamic performance. Internal fuel tankage within the wing demonstrated another aspect of the comprehensive design thinking that characterized the Mustang. The Americans had located substantial fuel capacity within the wing structure itself, using the space efficiently while maintaining the strength required for combat maneuvers and the high G loads that fighter operations demanded. This internal fuel capacity supplemented fuselage tanks and the external drop tanks that extended range even further for ferry flights and long escort missions deep into Germany. The engineers at Göttingen conducted their examination with professional thoroughness that reflected German technical culture's emphasis on detailed documentation and systematic analysis. They photographed the disassembled aircraft from multiple angles, created detailed drawings of key structural elements, measured dimensions with precision instruments, and conducted material analysis to understand alloy compositions and heat treatment processes. Every aspect of the Mustang received careful attention, from major structural components to minor fittings and installation details that revealed manufacturing methods and quality control approaches. Wind tunnel testing of captured wing sections provided quantitative data about the laminar flow airfoil's performance characteristics under controlled conditions. German engineers measured lift coefficients at various angles of attack, documented drag throughout the speed range, and mapped the pressure distribution across the wing surface to understand how effectively the design maintained laminar flow before transition to turbulent boundary layer occurred. These measurements confirmed that the Americans had actually achieved significant drag reduction through their laminar flow design, not merely in wind tunnel testing, but in an operational fighter manufactured in quantity under wartime production conditions. The testing revealed something else as well. The laminar flow wing, while providing exceptional drag reduction at high speeds, was somewhat less forgiving than conventional airfoils at low speeds and high angles of attack. The Mustang required relatively long takeoff runs and fast approach speeds for landing compared to some German fighters that employed more traditional wing designs. This represented a conscious design trade-off, accepting slightly more demanding low-speed handling characteristics in exchange for superior high-speed performance and extended range that made strategic escort missions possible. German test pilots who later flew captured Mustangs at Reich noted these handling characteristics in their reports. The fighter required pilot attention during takeoff and landing, rewarding smooth technique but punishing careless handling more severely than Messerschmitt Bf 109 seconds or Focke-Wulf FW 190 seconds that German pilots trained on from the beginning of their careers. But once airborne and operating in the high-speed regime where fighter combat actually occurred, the Mustang's performance advantages became overwhelmingly apparent through responsive controls, excellent acceleration, and sustained high-speed capability that made it extraordinarily effective in its intended role. The examination at Göttingen proceeded methodically through summer 1944, while Allied forces consolidated their foothold in Normandy and American bombers continued their relentless campaign against German industrial targets. The engineers working on Fraser's disassembled Mustang understood implicitly that their technical analysis, however thorough and professionally executed, would arrive far too late to influence German fighter development in ways that might alter strategic outcomes. Nevertheless, they continued their work with professional dedication, documenting Allied technical achievements with the same meticulous attention to detail that characterized German engineering culture regardless of broader strategic circumstances. The reports from Göttingen, combined with flight testing data from Reich and tactical intelligence from the Wanderzirkus Rosarius demonstration unit that flew captured Allied aircraft around operational Luftwaffe bases, painted a comprehensive picture of the Mustang's capabilities and the sophisticated engineering thinking that had produced them. German aviation designers absorbed these reports with professional appreciation for American technical achievements, even while recognizing that Germany's deteriorating industrial situation and resource constraints made replication increasingly impossible. Some German engineers proposed incorporating laminar flow wing designs into future fighter development programs, hoping to match American drag reduction achievements through similar aerodynamic approaches. Several ambitious projects explored these concepts during 1944, including advanced piston engine fighters that would theoretically combine laminar flow wings with powerful engines to achieve performance matching or exceeding Allied types. But severe material shortages, production difficulties caused by Allied bombing, and the rapidly deteriorating overall war situation prevented these advanced designs from progressing beyond prototype stages or entering operational service in numbers sufficient to influence strategic outcomes. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The Focke-Wulf Ta-152, a specialized high-altitude fighter that incorporated some lessons learned from examining captured Allied aircraft, reached limited production during the war's final months, but arrived far too late and in far too small numbers to seriously challenge Allied air supremacy. The Messerschmitt Me-262 jet fighter represented Germany's most successful attempt to leapfrog Allied piston engine performance through revolutionary jet propulsion technology, but chronic engine reliability problems, fuel shortages, and production delays limited its operational impact, despite impressive performance when flown by skilled pilots. Even the Me-262's technological sophistication could not overcome the fundamental reality that examining Fraser's Mustang at Göttingen had crystallized for German engineers. The Americans possessed not merely individual brilliant technical solutions, like the Laminar flow wing or the two-stage supercharged Merlin engine. They possessed the integrated industrial capacity, material resources, manufacturing precision, and systematic engineering culture required to translate theoretical concepts into operational aircraft, manufactured in overwhelming numbers with consistent quality under wartime conditions. The Mustang's Laminar flow wing represented more than clever aerodynamic design. It embodied a complete approach to fighter development that integrated advanced theory with practical manufacturing methods, quality control processes that ensured consistent results across thousands of individual aircraft, and comprehensive testing programs that validated performance before operational deployment. This systematic integration of research, development, and production reflected American industrial capabilities that Germany simply could not match, given its fragmenting economy, bombed factories, scarce materials, and depleted workforce. Doetsch's detailed technical reports, circulated through German aviation establishments during late 1944, reaching designers at Messerschmitt, Focke-Wulf, and other manufacturers developing new fighter types. These reports provided accurate data about Allied capabilities, dispelling some propaganda myths about inferior enemy technology, while confirming through systematic measurement what combat pilots had been reporting from actual engagements. The Mustang possessed significant and decisive performance advantages in the most critical categories for strategic bomber escort missions. The reports particularly emphasized how the Laminar flow wing contributed to the Mustang's exceptional range that made deep penetration escort missions possible. German engineers calculated that the drag reduction achieved through the Laminar flow design, combined with efficient engine installation and careful attention to minimizing parasitic drag throughout the airframe, resulted in fuel consumption at cruise speeds substantially lower than German fighters of comparable power. This efficiency translated directly into extended range that allowed Mustangs to escort bombers to Berlin and beyond, fundamentally changing the strategic bombing campaign's viability. German fighter designers studying these reports recognized that matching American bomber escort capabilities would require comprehensive redesign of existing fighters or development of entirely new aircraft, incorporating similar efficiency principles. The Bf-109, despite numerous refinements and engine upgrades throughout the war, retained fundamental design characteristics established in the mid-1930s that limited how far performance could be improved through incremental modifications. The Fu-190, though more modern in basic design, likewise faced constraints from design decisions made before advanced Allied fighters like the Mustang appeared over Europe. Creating competitive long-range escort fighters would demand starting fresh, with clean-sheet designs, incorporating laminar flow wings, efficient cooling systems, adequate internal fuel capacity, and powerful engines with sophisticated supercharging. This level of comprehensive development required resources, time, industrial capacity, and stable conditions that Germany no longer possessed by late 1944 as Allied bombing intensified, material shortages worsened, and the overall strategic situation deteriorated beyond recovery. The engineers examining Fraser's Mustang at Göttingen operated within an increasingly surreal environment where professional technical work continued even as the strategic context that gave it meaning collapsed. They documented American engineering achievements with scholarly thoroughness, while Allied bombers destroyed German industrial capacity, measured wing profiles with precision instruments, while fuel shortages grounded Luftwaffe fighters, and wrote detailed reports while the Reich's remaining resources were consumed trying to hold back advancing Allied and Soviet armies. Some of the engineers involved in examining captured Mustangs would later reflect on the profound irony of their situation. They possessed the technical expertise to understand exactly what the Americans had accomplished and could appreciate the sophisticated engineering thinking that characterized the Mustang's design. They recognized the integration of advanced aerodynamic theory with practical manufacturing capability that made the fighter so effective. But they worked within an industrial and military system that could no longer implement the comprehensive solutions required to counter Allied technological and numerical advantages, regardless of how well German engineers understood the technical challenges. The captured Mustang at Göttingen provided German engineers with a window into American aviation technology that revealed capabilities exceeding what fragmentary combat reports and propaganda had suggested. The Laminar flow wing represented just one element of a comprehensively engineered fighter that integrated multiple technical advances into a highly effective operational weapon system. Every aspect of the design, from the efficient wing to the powerful supercharged engine to the carefully streamlined fuselage and innovative cooling system, reflected systematic attention to detail and optimization that accumulated into decisive performance advantages. German test pilot Hans-Werner Lerscher, who flew numerous captured Allied aircraft during the war, including several P-51 variants, later described the Mustang as disconcerting to fly because of its unfamiliar cockpit layout, with numerous controls and switches that seemed unnecessarily complex compared to German fighters like the Bf 109, where everything was simple and close to the pilot. But Lerscher acknowledged the Mustang's fine handling characteristics and impressive performance, noting particularly its speed, range, and effectiveness in the air combat role for which it was designed. Walter Wolfram, another German pilot who flew captured P-51 seconds, expressed similar observations. The aircraft felt different from German fighters in fundamental ways that extended beyond simple matters of cockpit layout or control response. It represented a different design, philosophy that prioritized range and high-altitude performance over some other characteristics that German fighters emphasized. These differences reflected divergent strategic priorities between the Luftwaffe, which needed fighters primarily for homeland defense, and the American 8th Air Force, which required long-range escorts capable of protecting bomber formations throughout missions deep into enemy territory. The examination of Fraser's Mustang concluded during early autumn 1944, after German engineers had thoroughly documented every aspect of the aircraft's design and construction. The technical reports they produced provided detailed analysis of the laminar flow wing's geometry, surface quality, structural design, and integration with the rest of the airframe. These reports joined similar documentation of other captured Allied aircraft types in German technical archives, representing the systematic intelligence-gathering efforts of a professional military organization attempting to understand enemy capabilities even under desperate circumstances. Some of the engineers who examined the captured Mustang would survive the war to continue their careers in post-war aviation, applying hard-won expertise to new challenges in a transformed world. Klaus Doetsch himself would later work on post-war German aviation projects, his knowledge of advanced aerodynamics gained through years at Göttingen, finding new applications in the jet age. The detailed measurements and analysis conducted on captured Allied aircraft during the war would inform German understanding of advanced aerodynamic concepts that influenced post-war aircraft development despite the Reich's collapse, and Germany's temporary exclusion from independent aviation development. The fate of Fraser's specific Mustang after the Göttingen examination remains unclear in historical records. The aircraft may have been reassembled and transferred to Rechlin for flight testing, used as a static training aid, or simply scrapped for materials as Germany's situation deteriorated during the war's final months. Many captured Allied aircraft were destroyed during the chaotic final phase of the war, as Germany collapsed under simultaneous pressure from east and west, their ultimate disposition lost in the confusion of military collapse and occupation. Lieutenant Thomas Fraser, whose forced landing on D-Day had delivered his fighter into German hands for technical examination, survived his time as a prisoner of war and returned home after Germany's surrender in May 1945. He likely never knew the detailed technical analysis that German engineers conducted on his aircraft, or how thoroughly they documented the laminar flow wing that contributed so significantly to the Mustang's exceptional performance. For Fraser, the P-51 had been simply his assigned fighter, a machine he flew in combat without necessarily understanding all the sophisticated engineering that made it so effective. But for the German engineers at Göttingen, who examined that fighter with professional thoroughness, Fraser's Mustang represented something more profound. It embodied American industrial capability and engineering sophistication that exceeded what German propaganda had claimed about technologically inferior enemies. The laminar flow wing, manufactured with precision that German production methods struggled to match under wartime conditions, demonstrated that American aviation technology had reached maturity, rivaling or exceeding German achievements despite starting from arguably less advanced positions before the war. This recognition, forced upon German engineers by direct examination of captured equipment, carried implications that extended beyond technical aviation matters to questions about overall industrial capacity, manufacturing quality, engineering culture, and the integration of theoretical research with practical application. The Americans had not stumbled accidentally into producing an exceptional fighter. They had systematically developed the Mustang through careful research, sophisticated design, precision manufacturing, and comprehensive testing that validated performance before operational deployment. The examination of the Mustang's laminar flow wing at Göttingen during summer 1944 represents a small footnote in the vast chronicle of World War II's air war, a brief moment of technical intelligence gathering that produced detailed reports read by relatively few people and influenced strategic outcomes not at all. But this episode illuminates broader themes about how professional military organizations attempt to understand enemy capabilities through systematic analysis, even under desperate circumstances, when such knowledge arrives too late to alter inevitable outcomes. German engineers approached captured Allied aircraft with scholarly thoroughness that reflected professional competence and intellectual curiosity, regardless of strategic context. They documented what they found with meticulous attention to detail, creating technical reports that accurately characterized Allied engineering achievements without propagandistic distortion or wishful thinking. This professional integrity in technical assessment contrasted sharply with propaganda claims about inferior enemy technology, revealing the gap between what German experts understood privately and what political authorities proclaimed publicly. The Mustang's laminar flow wing confronted German aerodynamicists with undeniable physical evidence of American engineering sophistication embodied in carefully shaped metal, manufactured with precision that made theoretical concepts work in practice under operational conditions. This was not fragmentary intelligence from dubious sources or second-hand reports from combat pilots whose observations reflected chaos and confusion. It was the actual aircraft itself, disassembled on examination tables where every dimension could be measured, every surface evaluated, every structural detail documented with instruments that did not lie about what they revealed. This direct confrontation with material reality forced acknowledgement that American aviation technology had achieved maturity that German propaganda consistently denied. The recognition came too late to influence German fighter development in meaningful ways, but it demonstrated how professional technical assessment eventually penetrates propaganda distortions when physical evidence becomes available for systematic examination by competent experts who prioritize accurate understanding over ideologically convenient conclusions. The legacy of examining Fraser's Mustang at Göttingen extends beyond the specific technical intelligence gathered during that summer of 1944. It illustrates how advanced aerodynamic concepts like laminar flow wing design transitioned from theoretical research to practical operational application through systematic engineering and precision manufacturing. The gap between understanding a concept intellectually and implementing it successfully in mass-produced operational aircraft proved wider than theoretical knowledge alone could bridge. German engineers possessed theoretical understanding of laminar flow aerodynamics comparable to American and British researchers. They had access to similar wind tunnel facilities and sophisticated testing equipment. They understood mathematically how carefully shaped airfoils could maintain laminar boundary layer flow across extended portions of the wing chord, reducing drag at high speeds. What separated theoretical knowledge from operational success was the comprehensive industrial capability required to manufacture laminar flow wings with sufficient precision and consistency to make the concept work across thousands of individual aircraft, rather than remaining confined to experimental prototypes and wind tunnel models. The American achievement represented by the Mustang's laminar flow wing thus embodied more than aerodynamic cleverness or theoretical sophistication. It demonstrated systematic integration of research, design, manufacturing, and quality control that could translate advanced concepts into operational hardware produced in quantity with reliable performance. This integration required industrial infrastructure, skilled workforce, material resources, and organizational culture that Germany's fragmenting wartime economy could not sustain regardless of technical expertise German engineers possessed. The examination of Fraser's Mustang crystallized for German aerodynamicists the fundamental reality that technical knowledge alone proves insufficient without industrial capacity to implement it effectively. Understanding what should be done provides limited advantage when circumstances prevent doing it. German engineers could measure the Mustang's wing profile with precision, document its exceptional surface quality, calculate the drag reduction achieved through laminar flow design, and appreciate the engineering sophistication represented. But they operated within an industrial system that could no longer manufacture competitive aircraft in numbers sufficient to contest Allied air supremacy, regardless of how well they understood what needed to be done. This recognition of the gap between theoretical understanding and practical capability marked a profound moment of clarity for professional engineers, accustomed to assuming that technical expertise translated straightforwardly into technological superiority. The Mustang confronted them with evidence that American industry had achieved integration of theory and practice, exceeding what German aviation establishments accomplished, despite arguably deeper theoretical foundations in aerodynamic research established during the interwar period. The final months of 1944 witnessed the Luftwaffe's systematic dissolution as an effective fighting force, despite continued courage and tactical skill demonstrated by surviving pilots. Catastrophic losses in experienced personnel, severe fuel shortages that grounded available aircraft, production difficulties caused by Allied bombing, and overwhelming enemy numerical superiority combined to render German air defense increasingly ineffective, regardless of fighter quality or pilot determination. The technical intelligence gathered from examining captured Mustangs and other Allied aircraft continued flowing into German aviation establishments, but this knowledge arrived far too late to influence outcomes or provide solutions to strategic problems that exceeded purely technical dimensions. The engineers who examined Fraser's Mustang at Göttingen operated at the intersection of professional competence and strategic futility, conducting rigorous technical work that documented enemy capabilities with scholarly thoroughness, while the broader military and political context that gave their work meaning collapsed around them. They measured wing profiles and documented manufacturing quality, while Allied bombers destroyed German factories. They wrote detailed technical reports while fuel shortages grounded Luftwaffe fighters. They calculated drag coefficients and analyzed structural designs while Germany's remaining industrial capacity was consumed, attempting to slow, but not stop, advancing Allied armies. This profound irony of professional expertise functioning within failing systems characterized much of Germany's late-war experience across multiple domains beyond aviation alone. German engineers, scientists, and military professionals continued performing their assigned tasks with competence and dedication, even as the strategic situation deteriorated beyond recovery, creating a surreal environment where high-quality technical work proceeded amid comprehensive systemic collapse. The story of Luftwaffe mechanics and engineers, examining Fraser's captured Mustang during summer 1944, thus illuminates themes extending beyond specific technical details about laminar flow wing design or aerodynamic efficiency. It reveals how professional organizations attempt to understand adversary capabilities through systematic intelligence gathering, even under desperate circumstances. It demonstrates the gap between theoretical knowledge and practical implementation when industrial capacity limits translation of concepts into operational hardware. It illustrates how direct examination of physical evidence forces recognition of uncomfortable truths that propaganda consistently denies. Most fundamentally, this episode demonstrates that truly superior engineering emerges not merely from brilliant individual innovations, but from comprehensive integration of research, design, manufacturing, and quality control sustained by adequate industrial infrastructure and resources. The Mustang's laminar flow wing represented American aviation technology's maturity embodied in precisely manufactured metal that made theoretical concepts work reliably across thousands of operational aircraft. German engineers examining that wing at Göttingen confronted undeniable evidence of engineering sophistication that commanded professional respect, even from adversaries who recognized its implications too clearly. The admission forced upon German aerodynamicists by systematic examination of captured Mustangs that American aviation technology had achieved exceptional integration of theory and practice through sophisticated engineering and precision manufacturing represented professional acknowledgement of adversary achievements unclouded by propaganda or ideological distortion. This acknowledgement came through direct technical analysis of physical evidence that could not be dismissed or explained away through wishful thinking. The laminar flow wing existed as measurable reality documented with precision instruments that revealed exactly what the Americans had accomplished. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.